Thank you, Fithia. So yeah, so first off, thanks to the organizers for making it hybrid. I mean, I know we always prefer to be in person when it's possible, but having the accessibility option is really good, especially when we have teaching and other things to do. So I'm very thankful for that. And I'll just briefly discuss, I guess, my relationship with Mark. So I think I met Mark first as a graduate student. I think the first time I met him in person was maybe at a workshop in Naramata. Very nice workshop. We went for a nice hike up on the Kettle Valley Railway, I think there. And so Mark has always kind of served as, I guess, an informal mentor sort of through my career up to this point. I did spend a couple years in Edmonton, and I was very grateful for both Mark's and everyone in the math bio groups sort of hospitality while I was kind of working as a sort of a independent postdoc at that time. So yeah, anyway, on to the talk. So this is some work with a master's student of mine, Neha Bansal, who was expecting to complete sometime in August. That's why I put MSc minus 8/12. And we are studying, we're trying to establish a sort of notion of relative fitness or relative chance of success for models in which you can have more or less arbitrary kind of time-dependent parameters. Okay, so a little bit of motivation first. So if you take a population model that exhibits some kind of bounded persistence, so the population size doesn't go to 0, doesn't go to infinity, kind of remains bounded between the two. Then if you examine what's happening at the individual level, those individuals are experiencing what you would call sort of a near critical environment, right? And that's just by virtue of the fact that if you're at equilibrium, on average, every individual is having, one offspring, before they die, right? So, so for logistic growth, you have a per capita growth rate, R minus X, which is, 0 once it approaches equilibrium. If you take a more general model, say you have some population density, total population size that you can calculate, and suppose that you're able to write the sort of net reproduction rate as a function of the trajectory itself, then you have some sort of exponential integral formula for population size. And so if you have that, and if you assume that the population itself is kind of bounded between epsilon and 1/epsilon for all time, then if you look at the net per capita growth rate, then it is also kind of bounded between 0 and infinity. And so you could say that on average, it's close to 0, right? So in a pretty general sense for a lot of models, if you have this kind of bounded persistence, then at the individual level, it looks sort of like a critical environment. Okay. So if we view these types of models as kind of individual-based branching models, which I'm already hinting at, with some sort of density-dependent feedback given by, say, the trajectory itself and how it affects the parameters, is there a way of asking the question, what's the relative chance that kind of the lineage of one individual will be, say, the most successful lineage in the long run, right? Assuming that, say, they sort of compete and then you have one successful lineage. So this idea of decoupling a model and viewing it kind of as a branching model with density-dependent feedback, this goes back, we discovered, to work of Diekman, Gillenberg, Metz, and Tima from kind of the early 2000s. So this idea is not new, and it's been used to characterize equilibria for models for which this is difficult to do. And so there's some nice applications already for this idea. Okay, so if we just go to linear models, then this notion of kind of relative success can be captured by variously called, potential function or a fecundity function, or, just the right eigenvector of this matrix, right? So if I have a primitive matrix that describes, say, the mean number of offspring in a multi-type branching process, I'm using the probability convention so that Mij is what, the number of type J offspring of a type I, then the Perron-Frobenius theorem gives us some sort of a limiting result for the population over time. And in that result, the initial population is, you take the inner product with this potential vector to determine how much of the stationary vector that you get, right? So if you were to start from a single individual of a single type, I, then VI would describe kind of the relative success of type I in the long run. Okay. You can do this also for age-structured models, right? If you have a model with age-dependent birth and death rates, and the mean number of offspring from age 0 is 1, you can compute this sort of potential vector as the expected number of offspring produced in the remaining lifetime of an individual with age A. It looks something like this. And then you can, under reasonable sort of regularity conditions, you'd get some sort of result, quite analogous to Perron-Frobenius, right? Okay, so we have these potential functions for linear models, right? So if you have if you have a nonlinear model that converges to equilibrium or to a limit cycle, you might use that as a reference point and either use the equilibrium to just get fixed parameters, treat it as a linear model, or if you have a limit cycle, take some kind of return map, time t map, derive a discrete time sort of branching process from that, and you'd be back in the same situation. If, on the other hand, you only have bounded persistence and not much more information, you might still be interested to know whether there exists a notion of relative long-term success and how to characterize that. Okay, so that's kind of the starting point for our investigations. And so you might suppose that, okay, if it's time dependent, then instead of a fixed potential function, there's some kind of a time dependent one and a time dependent stationary vector, such that from any initial distribution, which, now it's important what the starting time is too, you get some sort of, limiting theorem such as this one, right? Okay, so this might be the sort of best case scenario for a time dependent model, right? Okay. And so in principle, determining this potential could depend on the full, complete future trajectory starting from that point, right? Because if it's arbitrarily time dependent, you might not know until, t equals infinity how successful it was, right? So there are ways of trying to shortcut that dependence. And this, again, is not a new idea. I did see it also in the aforementioned work, that in, say, for example, an age-structured model, age 0 serves as a renewal point in the sense that if you have offspring, those offspring are always born at age 0. And so you can use that as kind of a checkpoint at which you can stop things and then count them up and use that as a metric for the success of, an individual that starts at age A, right? So the presence of a renewal point is very useful. And this is used in, in probability theory to compute stationary distributions because it allows you to sort of close the cycle and actually get things that you can compute, right? So not a new idea, but potentially useful here. And the other thing that might be useful is that this kind of potential function is determined only up to constant multiples, right? I mean, if it's an eigenvector, of course, it's only determined up to a non-zero multiple, right? So it'd be enough to find the relative success from two different starting points. Okay, so we might be interested to know, if we run two trajectories from different starting points, is there a way to sort of couple them? Because if we can do that, if they overlap completely at some point in time, then they'll behave in the same way after that. Their relative success will be kind of the same after that. And so we could use that coupling time as sort of a checkpoint in the same way that we use the age 0 as a renewal point, right? Okay, so this is kind of the idea that we're looking to use. Okay. So coupling is a probabilistic technique that's quite useful. Here's an example with just two single particles, right? Say they're doing some kind of a Brownian motion or something. And with coupling, we say they run sort of independently, or at least they run according to their own respective probability distributions until they run into each other. And then after that, we require that they move together, right? So we can, this is a nice way of determining asymptotic properties from different starting points, because once the two particles are coupled, they are literally doing the same thing, okay? And so the question in this context is, can we make them couple? How long does it take to couple this? And right, okay. So the idea is to appeal to the stochastic branching model itself to try to see whether we can compute this sort of relative fitness. And to understand how this is determined, that potential function in the context of like a linear age structured model, it looks something, it can be determined by the limiting ratio of survival probability. Okay, so it's actually corresponds to that limiting ratio of survival probability. This is also the case for multi-type branching models. Okay, I gave a quick sketch of how this is true. I'm not sure how much detail I'll describe of this. So basically, if the survival probability goes to 0, as t goes to infinity, starting from age 0, right? So this means starting from age A1, starting from age A2 with a single particle. If the survival probability goes to 0, and if it varies slowly enough, then you can kind of condition on the offspring of one individual, right? And then recalculate after that point, what's your probability of survival? And if it's small, it'll be roughly linear in the average number of offspring that you had. And so that constant is just V of A itself, the expected number of offspring that you have, times S of t. So your probability of long-term survival is then roughly proportional to the number of offspring you were able to have before you died. Okay. So that relates the potential function to the survival probability. Some issues with this, if you want to use a stochastic process, is that critical processes tend to die out in finite time. So you're a little bit, you may not be able to couple them if they're already gone. So, and the other thing is that computing survival probability directly can be difficult to do. We're sort of looking for an existence theory, so we just want a method that kind of qualitatively works out, right? So here's where I'm expecting to lose some people, but that's okay. I'll try to keep you as much as possible. So we'll to deal with this, a trick that we use in studying branching models is just to bias the model, right? So if you take a critical model and you bias it on population size, so in other words, every time you have a transition, you tend to go with a slightly higher probability towards the larger than the smaller population. There's a way to do this that preserves the Markov property, so you still get a nice Markov process, right? So you can bias the model on what's called a martingale. It's just something that's constant on average. You can view it as kind of a fair betting scheme for the process. And then unbias afterwards to recover survival probability. So the way that would look for a critical branching process itself would be like this. You have a process that can increase or decrease by 1 in population at the same rate. Then the population size itself is a martingale because it's sort of constant on average, but it may go up or it may go down. And so you can just bias on population size. And when you do that, you basically get these factors proportional to how much larger or smaller the value got. And so you get a model where it's almost critical, but it tends to go up a little more than down. Okay, and that's actually enough to make it survive, because if the population size is 1, the death rate is then 0. And it also grows at a nice linear speed. So, I mean, you can kind of describe what this thing is doing pretty well, okay? So this model now survives for all time, and the measures are related just by, if you condition on information up to time t, you just take the original probability, multiply it by the population size you ended up with. Okay? So you can recover the survival probability by taking the expected value of 1 over z, if I just flip these around, with respect to the biased measure. Okay, so that gives you a way of calculating the thing that you're interested in, at least in the limit, by appealing to this biased model that survives, and we can hope to maybe describe what that looks like from different starting points and compare those values. Okay, so it would look something like, if we want to get this ratio of potential functions, right, then it would be the inverse ratio of whatever martingales you can come up with that you use to bias the model. And then the hope is that you're able to couple those respective processes. Okay. All right, so that's most of it. I'll take maybe 1 minute to do a little bit of detail. So in the setting in which we're studying this, we have a birth death. We have an age-structured model with arbitrary time-dependent rates. The martingale is actually a compensated population size, so you just correct it by the per capita growth rate taken as an exponential integral, and then you get something that's sort of constant on average, right? And this model will have a unique infinite lineage. Basically, the idea is that at criticality, to reach a big size, it's sort of the probability to get there is about 1 over the size, since it's constant on average. And so 2 lineages can only reach a big size with a much smaller probability than would be possible for 1 lineage to do it. Okay. So once you bias, you know you have at least 1 infinite lineage because it survives, and you're not going to have 2. Okay. So the idea is that with these 2 models, you'll have these infinite lineages, you'll have some extraneous particles. These are the 2 starting points. And then you hope to couple these sort of, we call them the spine particles, the spine lineages. So you hope that there's a certain rate at which these 2 lineages move to a newly born particle at age 0. And then after that, you need to deal with these extraneous particles. And so the basic claim that we have in that regard is that if I bias the model on a certain subset of particles with a certain kind of larger initial value, or if I bias it on the full initial value and condition on a certain subset of particles being the infinite lineage, I want these 2 measures to not be too different, because then that's what will allow me to compare different starting points and then hopefully try to sort of couple them together after a sufficient number of attempts. Okay, so that's yeah, a little bit vague, I guess, but probably about as well as I can do in 20 minutes. And so I thank you for your attention, and I welcome probably one or two questions, I guess. Yeah.